In this video, we will look at how to convert between simple expressions in infix form to reverse Polish notation form and vice versa, and be aware of why and where this form of notation is used. This video, therefore, is going to be tying together several different concepts. It will really help to ground the importance of post-order traversal and give you a concrete example of why it's useful. It'll also show you how another data structure, a stack, can become really useful when combined with binary trees. We've already seen in other videos that data structures work together. Arrays are often used to implement data structures, and we've seen how stacks and queues are used when we're doing traversal of graphs. So we're going to have a look now at the importance of post-order traversal and a concept known as reverse Polish notation. Let's give a bit of introduction. If we wanted to add two numbers together, say A and B, we would write it like this, A plus B. This is called infixed notation, because the plus part, the notation, is fixed in the middle of the A and B. We're all used to this type of notation. It's how we've been performing maths since you were taught in primary school. But what does the following mean? 2 times A plus B. Which bit do we do first? Do we do the A or B first? Do we do the times first? Well, we have to start applying rules like BODMAS, which of course you will have been taught in mathematics. Or we have to start putting brackets in to tell us to do the A and the B bit first before doing the multiplication bit. This is fine for us as humans, and we can follow these kind of rules and regulations. But computers find it ambiguous. The form of notation that we use, infix notation, without brackets becomes ambiguous, and computers find this difficult to deal with. A Polish mathematician came up with an alternative to infix notation by putting the operator at the front of the expression. So here we have our infix notation, but here, where we place the operator at the start, it is now called prefix notation, or Polish notation. This now reads as follows: add the numbers A and B together, instead of number A is added to number B. Now, the important thing here with prefix or Polish notation is that it has no ambiguity. In other words, we don't need brackets, and this makes understanding and working out expressions written in prefix notation a lot easier for computers to deal with. So remember, this prefix or Polish notation is because this symbol, the notation, comes before the two operands instead of fixed in between. If we reverse this and place the operators at the end, it's now known as postfix notation, or more commonly, reverse Polish notation. So this format here now reads as take two numbers and add them together. So in summary, we've got our standard infix notation, which is the way that we're used to writing expressions, where the notation goes between, prefix notation, where it goes before, and postfix or reverse Polish notation, where the operators go at the end. There are two main reasons why reverse Polish notation is so important in computing. Firstly, it's unambiguous and doesn't need brackets, and secondly, when we write calculations out in a computer using reverse Polish notation, we can use the power of the stack data structure to work out calculations. Let's have a look at this now. Okay, so consider this simple expression 3 times 1 plus 2. Now remember, from what we've said, computers aren't able to evaluate this logic. They need calculations to be presented in a simple left to right order. Here we have to use the rules of BODMAS or BIDMAS to know that we have to evaluate this part of the expression in the brackets before this part. However, in a computer using reverse Polish notation, this expression will be rewritten as 3, 1, 2 plus multiply. Here we can see how a binary tree structure is used to break up this expression written in infix form into a binary tree, and then by traversing this binary tree by using post-order traversal, we end up extracting the reverse Polish notation system. 3, 1, 2, plus, multiply. Now, exactly how we go from the infix form to this binary tree is going to be explained in more detail in part 2. However, for now what's important to know is the reason that this is useful, having this expression rewritten in reverse Polish notation, is now we can use a data structure called a stack to simply evaluate the expression from left to right. And we're going to have a look at that next. Remember that a stack is a last in, first out data structure. When we evaluate an expression written in reverse Polish notation, every time we hit a value, we push it onto the stack, and every time we hit an operator, it causes the last two items on the stack to be popped out and the result to be pushed back in. So, we start with 3, pushed onto the stack. Next is 1, pushed onto the stack. Next is 2, pushed onto the stack. We're simply working from left to right. We now hit an operator, plus. Plus causes the last two values to be popped out. That's 2 gets popped out, 1 gets popped out. The result gets calculated and the result gets pushed onto the stack. We then hit our times. That causes these two items to be popped out the stack, 3 followed by another 3, the result to be calculated and pushed onto the stack, and we're left with 9, our result, which we popped out. That'll be popped out when we hit equals. So you can see quite simply here and quite powerfully that combining things like binary search tree, postal traversal and data structures, computers are able to solve any calculation